Good afternoon, everyone, and welcome to the final talk of day 2 of Black Hat 2015. Just a quick reminder, if you would please remember to put your phone on vibrate during the talk. And you are now located in the Jasmine Ballroom for DOM Flow Untangling the DOM for Easy Bugs by Ahmed Nafisi.
Thank you. Nice. Thank you. Thanks for being here. It's always scary to give a talk right after someone has given a talk on hacking MacBooks using USB cables, the SID2 version. Anyways, I'm just using HDMI, so let's hope nothing bad happens. So just to set the expectation for today's talk, for those of you who doesn't get to understand the context of the DOM here, DOM flow, or the DOM bugs that we're talking about today, it's not going to be anything about memory corruption bugs. It's more about the browsers, JavaScript, the DOM API, and some interesting nuances around that area. So about me, I'm Ahmed Nafis. I work as a software security engineer for a startup in San Francisco. I've been speaking at a few conferences for some time, mostly about web AppSec. And I usually like to play the defender role, try to defend things. I believe that's much more harder with the emerging attack trends that comes along, especially in the browsers. So the overall talk today is going to be something about how are the modern web apps evolving on the front end, and especially their problems with respect to penetration testing them, and then talk about a couple of tools that I've written to help understand and analyze those certain bugs that we're going to talk about, and then of course a few instances or scenarios where new kind of bugs could emerge and how we can catch them. So if you see most of the web apps today, they're going to be more and more using front-end libraries like React, Meteor, whose purpose is to make things simple for the developers. They contain a lot of logic within them, and the existing penetration testing tools are written especially for attacking web apps, the traditional web apps. But the modern day web apps are more and more using these libraries. For instance, if you take Meteor, they have their own protocol which does some WebSocket communication, a two-way bidirectional communication. And if you need to write your own protocol, if you need to write your own tool to understand what's the communication which is going on between your server and your client, it can become a little harder with the existing tools. So I'm not going to talk specifically about any of these, but I'll give an overall idea about what we can do and what we should be looking forward in attacking web apps. So one thing, as I already mentioned, like these frameworks which are already complicated, and static analysis on them is pretty hard. If you run static analysis on, for example, the Google's front-end code, they won't understand anything. Even if you beautify them and send it to static analysis, there's a lot of stuff, closures, some different kinds of compilers, a lot of things happening there. And again, the complex frameworks, which includes things like JSX, like React.js from Facebook, uses something known as JSX. If you've been hearing about XSS, the classical XSS, by which I mean the reflected XSS, was a problem that have been haunting us for the past 2 decades, in which the vulnerabilities occur when you have JavaScript injected into a HTML context. And I'm not so sure that we as a security community or developers have completely addressed them, but now we have another beast where things like JSX, where you can inject HTML code inside JavaScript, right? The inverse of that. So things like JSX comes from an existing technology called ESX, which was used in Firefox way back. But with this, things are going with your own DOM and own parsing and compilers, which all these libraries brings into the picture, things are going to be much more complicated. So let's talk specifically about DOM XSS. Just to give an overview of what an XSS is, it's a certain bug which, due to some failure in input validation or output encoding, you could have attacker's code running on your front end. And as I would always like to define cross-site scripting is, when someone else runs code on your web app, it's not your web app anymore, especially the front end with all those logics. Now, the specific case of DOM XSS is where an XSS is triggered mostly or completely due to your front end code, wherein your attacker's payload doesn't even goes to the server side. Everything is executed on the client side, especially using the DOM APIs and the browser components. So to understand more about DOM XSS, people usually refer to the classical thing of how data flows using source and sinks. So in today's talk, when we talk about sources, we are going to talk about any entry point where an attacker can inject data. And a sink is where the same untrusted data gets to execute directly or indirectly. So cool. So let's see a very classical DOM XSS example, or the hello world of DOM XSS, as most people would put this as when they're trying to explain what a DOM XSS is. Here we have a location where it says some website.com/something, and then you have a hash and then a name, something like Mark. And you have a JavaScript code which tries to take the hash of the current URL and then tries to do some filtering on that, takes that and writes it into your DOM using the document.write. So in this case, as it's pretty obvious, the document.location.hash, the location here becomes a source, and which is the entry point for the attacker, as an attacker can directly control that part. And a document.write becomes the sink. So this is a pretty easy way of having a DOM XSS. And there are, of course, a few web apps today which still have vulnerabilities like this, pretty simple, even with eval. So during the past Black Hat talks, we have seen some amazing research in terms of DOM XSS and how prevalent they are and the kind of tools which have been used in taming them. So Sebastian, Ben, and Martin, they've done this research on 25 million flows later, where they took the Alexa's top 1,000 or 10,000 websites, and then they tried to run their own instrumentation engine on that using some crawling, and they found the most commonly used sources and sinks. So this is a pretty big issue, and developers even today, or when they try to keep moving fast with their front-end code, these kind of bugs can be easily introduced, wherein if you don't understand what your sources and sinks and your DOM APIs are doing, then it can be pretty bad. So why do these kind of problems come into existence? So it's a common software engineering problem, or I would like to say the printf anti-pattern, right? So where you try to mix code and strings together, and you end up with problems like this. So even frameworks, for instance, AngularJS, have some ways of executing code directly from a string, even though eval can be disabled using strict JavaScript parsing, things can still go wrong. That is specifically because the DOM specification, the DOM APIs, are pretty rich at doing this string to code conversions in a direct or indirect way. So when I mean the direct ways, it's pretty obvious. We have been hearing JavaScript in eval is evil for a long time. People have kind of stopped using that, but we still have other things like the function constructor, where if you replace the string here would be an X, where you could have any kind of code execute, and or even it's script, set timeout, set interval, a lot of other APIs which directly executes code. And the most interesting ones to me are the indirect DOM APIs which converts string into code. Something like jQuery's selector API. It's the dollar of whatever string you give, or the document.write. So the document.write here itself is JavaScript. It's a DOM API, it's JavaScript, but it can take string and put it as HTML. That means it can push stuff into the DOM. Now, at the same time, the DOM can execute JavaScript if you give certain conditions. So ultimately, this is an indirect way of executing code, executing JavaScript using JavaScript itself. And various other examples which is pretty obvious if you have been around the DOM XSS world. They have just given a few examples of the direct and indirect DOM XSS cases. So the specific example of jQuery's selector, where the jQuery's most important documentations, or when you see Stack Overflow or the top page of jQuery, the one which is advertised, or people know jQuery for selectors, right? So if you start something with hash, it can select the IDs in the document. It does the equivalent of document.getElement by ID. If you do something with dot, it does look for elements with class and returns an array of elements which has those class as its class name, or even tag name. But the same selector can also be used to inject HTML content onto the DOM. If your string doesn't start with a dot or a hash, and if it's something like an image src equals something, or some script src equals something, it just injects that into the DOM. And it has been known for a long time, but what I'm trying to say here is the indirect ways of executing code in your DOM, which most people are not, especially the developers, are not aware of. So with all these being said, and with a few tools which are already trying to find all these bugs, why is it especially hard to find these kind of bugs in today's web apps? This is because usually your web apps, when you look at the view source of pages, they're going to look something like this, which if you try google.com and see the view source, it's going to look something like this. Facebook, something like this. And even if a website completely adopts CSP and then you have all your scripts embedded inside, script tags, and being properly loaded from whitelisted sources, even then the JavaScript is going to be minified, compressed, and will have a lot of complexity involved with this. So I had this problem. I didn't want to look at code like this. Rather, I wanted to have an understanding of how the web app is by just doing something with the web app, right? Rather than doing some static analysis. So I've been using a few of these tools, especially the Dominator Pro, for a long time, but there have been a few complexities in setting it up and doing things the Dominator Pro way. But by far today, it is the best DOM XSS scanner that I'm aware of that can find vulnerabilities by doing some dynamic tainting. And there's also this research by the paper that I just showed, Sebastian Ben Hawks, where they patched V8 and the Chromium and open source. They patched the Chromium web browser to kind of track all these sources and things and come up with those results. But I'm not sure whether they made it public, and it's not in a usable form. So it's a problem for pen testers. And even static analysis, I said, they can be useful in some cases, but I'm not a big fan of regex and simple string matches trying to find vulnerabilities in complex web apps. So I thought of a way. So what can we look for? Just in addition to DOM XSS, I found like, okay, it's not just the DOM XSS, the source to things which flows, that's the problem. There's also various other problems which can be found on the DOM, some logical bugs, or people using methods where it wasn't the appropriate method. So as I said, these are the kinds of things that you can find with the DOM injection. You can have something like a DOM-based open redirection, wherein the server doesn't even get to know what kind of code you're injecting or what kind of redirect you're trying to do, especially useful in advanced open redirections where if someone is doing some specific spear phishing and stuff like that, a DOM-based open redirection is a pretty good thing to do, because even if you have bots or stuffs doing on your server side, sitting on the server side, they wouldn't get to know what's happening, right? And things like web storage manipulation, every kind of HTML5 API manipulation, local storage, WebSockets, things like that. And specifically, I wanted to talk about the second-order DOM injection. So this is a common thing which is mostly missed by the usual DOM XSS scanners. Because of the fact the source actually comes very delayed. So by second-order DOM injection, I mean it's more like a second-order SQL injections that we used to hear the term. So rather than having a source and sync directly on the DOM, your source is somewhat delayed in the sense they're coming from a persistent storage. For example, today you register for a website and you go and store your username. And after 5 days, someone writes a vulnerable code which uses a sync, and where the source here is an XHR response which comes from a database, right? So people haven't thought about XHR responses as a possible DOM source. I mean, we know that's a problem, but like the tools have not been so good with finding these kind of stuff. So. And also things like globally exposed variables in the DOM. We have been hearing cases of, hey, you shouldn't be actually doing globally exposed variables. That's a bad idea. It's a bad JavaScript practice. It can cause bugs. But we have rarely seen problems which can have security issues with that. So I recently came across an issue where actually a global variable in combination with DOM clobbering can actually be an issue. And usage of certain methods, which the ECMAScript 5 specification has some very quirky behavior in how they define certain methods. So we'll go over one of the methods and talk how to find these how to find these functions using the tool. So yeah, of course, the tool I've been talking about is I've written a Chrome extension called Hookish. It's basically to find and analyze and examine how your current web app's DOM is and what kind of things can go wrong. And basically, it's like reverse engineering a web app. So you kind of get to understand what's happening. So if you're from the OS world, if you need to know what an app does without doing much static analysis, you go and hook into all the registers or all the APIs, the DLL injection, stuff like that. So I'm kind of trying to do something similar in the world of Chrome extensions and JavaScript to make use of it and have dynamic analysis. So let's take a look at it. Okay. Okay. So it's a Chrome extension you can install from the Chrome store, and we have this thing over here. So yeah, this is like the panel that I have for Hookish, and here you can have all these different kinds of APIs that you want to hook or override and redefine and analyze. So let's try to look at an website like Facebook, right? As I said, so I believe I shouldn't be logged in. Yeah, I'm not. But there you go. So yeah, this is the problem I've been talking about. So most of the web apps I see today while pen testing, they look like this, which is pretty annoying to me. So, or any pen tester for the matter. So I go here, give Facebook. So now what happens is Hookish stops running on Facebook.com right now, and it starts hooking into all the different sources and sinks and starts reporting back to the app. So in this page, I just loaded Facebook and I just navigated through it. And all these cases are actually may not be vulnerable cases. Of course, I'm not going to show you a Facebook vulnerability right now, but the thing which is interesting, which I wanted to see was what are the values being passed to different APIs, and how are the sources and sinks being called. So for example, here, as you can see, this thing called DOM nodes. So by DOM nodes, in the context of Hookish, it means anything like element.innerHTML or element.outerHTML, anything which has to do with a DOM nodes property, which injects stuff into the DOM. So in this case, as you can see, an HTML element called div class equals something. The gender form has been injected. So this is using, probably this is because one of their libraries trying to do stuff and instead trying to do stuff dynamically. So for most of the cases, you won't find these kind of things which are dynamically injected as part of your source code. So these are the things I was interested in looking while pen testing an app. And also things like what kind of values are returned to document.cookie. And from here, if I see something is interesting, for example, I see, okay, the document.cookie is being set to a certain value at this point. So I want to know at what file and what line is this thing happening. So here you have a small stack trace which tries to show you, okay, at what line and what point is this thing happening. And if you just click on it, you could, So this directly integrates with the Chrome's console. So if you just click on it, it just directly takes you to that page. And you can kind of analyze the methods which are being called and get a function call trace of how are these methods called and when. So with that being said, I'd also like to talk about a POC app I made for specifically testing these bugs. A few of the bugs are that I'm going to talk about today. So it's called damnvulnerable.me, and it has different examples or scenarios. So if you have been in testing DOM XSS for some time, you must be knowing things like, let me check. Google's public firing range .appspot. It's a publicly available sources of collection of sources to sinks, and if you have a DOM XSS scanner, you can just run it against this and navigate them. And your DOM XSS scanner is good if it can find all these issues on the fly. So I've taken a few examples of that, and then a few examples of my own about the certain different DOM bugs that I talked about. So let's get into it in more detail. So that's damn vulnerable. Okay, so I kind of explained how Hookish works by giving an analogy to how you would reverse engineer native apps by doing DLL injection. So here, in this case, I've written a library called DOM hooks, so which tries to track all different sources and sinks, and it injects them into the page before. So this is a Chrome extension, and it tries to inject them into the page and wait for the page to load, and then you track the sources and sinks. So this is the high-level view of it. So as you can see, the Hookish green bar over here is the extension, and you have a web app with its own DOM. And one of the things that you should, when trying to do something like this, is you should be careful that you don't mess with the already existing DOM. Otherwise, the existing web app won't work properly, right? So you want a completely isolated context, and Chrome's extension gives you exactly that. Due to some security reasons, they already do extensions already run in an isolated context. So Hookish just takes all these DOM hooks and then registers all these hooks, for example, document.write, and sends it to that web app's DOM. And now what happens is the web app's JavaScript code runs after this. So that's just like a DLL injection. Everything that the web app calls would be registered by the already existing registers that we have placed. Also, you could use something like ECMAScript's object.freeze, which make sure that your overrides are being maintained. Now, you can also ask delayed questions, right? So once the web app has loaded and the web app has reached a certain state, you can ask questions like, okay, give me the list of all global variables that your DOM has currently exposed. Things and various other interesting questions like this. So I've written these DOM hooks.js in a modular fashion. So if you're like interested in trying to do fuzz testing or even writing DOM-based ideas or things like hardening your DOM, it can be interesting to you. So here are a few ways of redefining how you would redefine our override in JavaScript. So I've used the basic properties here, and for instance, you have if you have a method like a window.alert, which is a method, you would just have a copy of it and redefine and override it, or also use for certain properties like cookies. So cookies are interesting properties. You cannot just go and say, have a copy of the cookie and then create a new cookie proxy out of it. You want to, if you say document.cookie equals a equals 123, you set a cookie with the name a and value 123. The cookies setter already has a logic which tries to push these cookies into the cookie jar. So you can have something like, so what you can use here is lookup getter or lookup setter for cookie, and then redefine them using define getter and define setter. So if you have been involved in JavaScript overriding, these things must be kind of familiar. So an interesting thing happened. So a couple of months back, while I was testing my tool, all of a sudden, one of the registers stopped working. Right, one of the hooks just won't work. It won't. I was not able to override it. And then I researched and what happened. And then I saw there was a patch which came which disabled which disabled overriding of location and things like document or domain. So, and I remembered actually a year back, I gave a talk at Black Hat Asia about how you can use this overriding itself for insecurity, right? So just by overriding document or domain, at that time the OWASP CSRF guard, the Java CSRF guard library can be completely bypassed from a cross-domain website. So someone can read the CSRF token from a cross-domain website by saying I am a gooddomain.com by spoofing document.domain. So at that time when I filed the bug on Chromium Bugs, people are not so interested in fixing them because it was more of a web apps problem. That's what they thought. At that time, Safari was the only one which had that fix, and Firefox and Google were not so serious about it. But if you see, redefinition has been an interesting problem recently. So if you have been in Natasha's talk yesterday, redefining ECMAScript properties and how she used the same stuff in ActionScript as well. So it's been an increasing problem, especially for security. But at the end of the day, the web app or the developer has to implement all these things properly with keeping these in mind, so they don't break their web app's integrity. So that was an ironic story. A couple of years back, I used the same properties for insecurity, but today I'm trying to use them for security, and it's not working out. I mean, part of it is not working out. So I use a tool called DOMStorm, which I've written. So this link basically gives you all the location properties which can be overridden in Chrome right now and various different browsers. So the tool I'm talking about is DOMStorm. So it is a database of all of interesting questions that you can ask to a browser and track them across different versions of different browsers. So for instance, you might find a bug in Firefox and you have a POC for that, but you know at the same time, as of this point in time, it doesn't work in Chrome. You can have a database for that, and it just keeps running the tests and tries to tell you when something goes wrong in different browsers. So as you can see. So let's try to look at the location properties. So a year back, this column was full of red, which means none of the location properties can be overridden. The is configurable was true, and in the latest Chromium browsers, this is different. So if you run it on Chrome 42, I believe, these results will be different. Yeah, and of course you can track this across different browsers. Yeah, and for different, so for certain properties and certain different OSs, the results may vary. So let me get back. Yeah, and another interesting thing I would like to show is, I forgot that. How about window? So while working with bypassing filters, XSS filters and stuff, so you might, in certain cases, your DOM properties might be filtered. For example, in one of the instances, I was not allowed to use parentheses or the word terms like window or top or any object which refers to window. So I wrote a module which, not me, one of my Twitter friends, Pepe Villa, he wrote a module which lists the constructors of window without parentheses. So just a second, So all these things in Chrome would refer to a window object which you can access without using a parenthesis. So these kind of interesting things can be tracked across different browsers. Of course, you have to fuzz them on each browser to get the results. So that's it. Let's move on to how DOM flow works. As we talked about, we have this DOM hooks which are into every sources and sinks possible. So right now, any source which gets data, Hookish knows about it. So if a data comes, the source knows my overriding function takes note of it and adds a specific flag in different methods. So one of the methods is by just changing the value or prepending or appending depending upon the context in which the code is used. So here I would say, okay, so this location has been called and I'm just adding a flag to it. So whoever sinks who tries to get this result might get the data. So one thing to note here is, of course, this level of tracking the sources to sinks is nowhere close to how you would be doing in a native level or V8 level taint tracking. So that's the most exhaustive and complete way of doing analyzing sources to sinks. But this kind of helps you understand most cases of sources to sink flows. And then the tainted data can go through different filters, so which can be a JSON.stringify or JSON.parse, things like substring. It can go through a lot of logic. Even the whole string can be lost, and you can have a completely new string from it. So, and then it goes into the sink. So whenever a sink receives data, our sink also knows, okay, so if this has gone through a source which has already been which has already had a flag attached to it, then you can kind of tell whether this piece of data has taken this path or not. So thinking of a simple example, so every time, for instance, if you have a document.cookie which goes through different methods and ultimately ends up in some div.innerHTML. So every time the cookie is accessed, that specific data is marked with or tagged with a flag which says, okay, I am doc cookie with a certain flag, and it goes through transformations, and ultimately when the inner HTML's sync registers look at this, they understand what's happening here. So that's one way of doing it. In certain methods, you have to make use of JavaScript's boxing property. So in JavaScript, if you have a literal string like str equals hello, and say type of str, that would be string, the literal JavaScript string. Now you can add a property to that string. It's because we know the mother of everything in JavaScript is object. Now you can still say, okay, str.flag equals true, and if you still say type of str, that would still be string. But if you access str directly, that would be a string. But if you say str.some property, it would have the flag. Yep. So let's see more about how I generate this source to sync stack trace. So I was able to make use of V8's powerful stack tracing method, which is also available in Chrome. So if you deliberately throw an error at a given line of code, then it actually gives you an error.stack, which tells you at this line, okay, this error has happened at this line, and here's the stack through which I have been called, or the line above me have been called, and it just gives you the stack. And it easily integrates with Chrome's DevTools, as we saw. You can just click on the links and go and navigate what the files are. And also, in using it in complex real-world applications, you have to blacklist a lot of things. For example, if you just simply do this on all sources and syncs on all web apps, it would give you a lot of stray information that you might not need. For instance, if your web app at some point is using Google Analytics, then your GA.js code just comes in and sticks into this stack. So you need to look for all these stuff and blacklist them. So with that being said, I will go through 4 interesting scenarios and use the Hookish tool to find web app bugs. So let me go through that quickly. So the first thing is something which I kind of talked about already, is which most pen testing tools miss is your XHR's response or your WebSockets response, and how they are being populated into the DOM. So I always used to wonder when a web app is using some API and fetches some JSON content. I always used to wonder, okay, what's going to happen to this JSON content? Because regardless of what's happening on the server side, they might be doing proper filtering and output encoding. Regardless of that, the ultimate choke point is what your JavaScript is doing before pushing it to the DOM, right? So and an example for that would look something like this. So you get a response. So this is a second order DOM XSS. So you get a response, you do a JSON.parse, your response, you take a certain part of your response and then push it into the DOM, right? So this can become interesting while you're dealing with Hookish, especially because your SHR.response text is no more directly injected into the DOM, but a part of it is injected into the DOM. But in most of the cases, when you deal with JSON content, most of the apps usually use JSON.parse. So you have your JSON.parse here as a filter. So if you also hook into JSON.parse and kind of give the data that you want to give so that all other Hookish components can know, okay, this has gone through this flow, then you can easily identify these kind of vulnerabilities. So yeah, let me show. I'll just try Hookish on damn-vulnerable.me, and yeah. Cool. So it's just the internet. Okay. So yeah. So this is an example of a JSON response being injected directly into the DOM. As you can see here, it's kind of like the same code. So this is the vulnerable script. Yeah. So this is the vulnerable line of script. This is where the actual DOM XSS takes place. And so you can pretty much tell from just by looking at the code, this is a proper DOM XSS. So if you look into Hookish, things which are specifically which Hookish can find that, okay, this can be a really interesting or serious issue, or can be possibly a DOM XSS issue, it's going to give you a different look of it. It just highlights that, and it also gives you the line, and so it's in div.innerhtml.js. On line 16 is where you actually have to fix this. So the interesting thing here is this mechanism of testing for web apps by doing all these things it's not just directly useful to the pen testers, but it can be directly used by developers as well. So if you see developers, when they try to go and push some code, before they do all this, they try to do the local changes, and they actually try it on their web app on their local site. So when they do that, if the developer has something like this enabled on the fly, and he can keep browsing his website, or he can keep testing his new feature, as and when these vulnerable components comes into the DOM, Hookish alerts the developer and tells, hey, you have something going on wrong. Because one of the fundamental problem with scanning or finding web app bugs is actually the code path to take. So if you give a whole new app to a pen tester, and hey, okay, go and pen test this app, he might try out the natural spidering way of doing things, and he tries to understand the web app by looking at it a little bit, but it cannot get as much closer as a developer knows the web app. So, and he doesn't have to do anything extra, he just integrates with it. So this can be pretty useful to developers, and if you integrating tools like this into the developer workflow will actually help. So yeah, as you saw here, so this Hookish was able to identify the vulnerability, and also for penetration testers who are more interested in finding these kind of bugs, they can just use DOM flow. I have a different interface for that. So okay, this can be things like, okay, I want to find sources like XML HTTP request, WebSocket, or even document.name, which leads into inner HTML. So yeah, and it tells you whether what kind of, it just gives you an alert, but at the end of the day it finds everything and logs them into the console, and he knows where the vulnerability is from this. So that's pretty useful too. So yeah, this is basically using JSON.parse as a filter and giving the Hookish intelligence to that. The second one is kind of interesting. I'll have to just go through this pretty quickly. I have 3 more cases to show. So yeah, so most of us would have been aware of iframe sandboxing. Iframe sandboxing is it's an HTML5 concept. In addition to the normal iframe, the sandbox would execute in a null origin, and if you want to run untrusted code in your web app in your domain, then you can just use this, And even if you want to enable scripts or disable scripts, all these kind of controls are available using iframe sandbox. So as you can see here, you have a trusted parent window. Think of websites like JSFiddle, CodePen.io, things like that. And then you have an untrusted sandboxed iframe child, which by default, the origin would be null. And you just say, I just need access to allow scripts. So any script that this iframe would execute would actually be executed, but in the context of the null origin. So I have so this is the explanation of what an iframe sandbox is. I'm just not going through it. But yeah, I have an example of this written as a code in DAM vulnerable. Just go through that pretty quickly. Oops. Yeah. So this is the parent domain, which is the trusted one, and then you kind of give a payload through the parent domain, which should take that data and execute as script in the iframe sandbox. So here's the code which does that. So the actual bug is in this, where you do a window.onload, and then once the page has been loaded, you try to create an iframe sandbox on the fly, and then take this user input and then inject it into the iframe. And at the same time, your parent page has a code which executes secure code. So for example, if someone is able to execute this line of code, then he has actually broken the sandbox. It's equivalent to breaking the sandbox in this case. Because he's executing code, the challenge here is to execute code on the iframe window, but it should affect something in your parent window. So here, if you see, the global variable is of course secure_flag, which doesn't have a declaration. The developer just made a mistake by doing, okay, secure_flag equals true. Now, and this condition can only be executed if the window.inferno method can be called, but this cannot be called until unless you are executing code in the same domain. Hope the explanation helps. So here, the actual payload would be something like whatever the user gives here would be executed in the iframe sandbox, and yeah, you just broke out of the sandbox. So I was able to run script in this iframe, which actually affected this. So let's see what's happening here. So this was the initial scenario. We have the trusted parent window, the untrusted parent window, untrusted child iframe, and initially there was no window.name for this iframe, right? This sandboxed iframe. Now I was able to execute any script in this context. So I set a name equals secure_flag. So by default, everything in JavaScript on the DOM is executed is on top of window object. So here it would be window.name equals secure flag. So this iframe's name now becomes secure flag. Now, because this iframe's name is in secure flag, in the DOM, usually the parent windows and the child windows, one of the things that being shared is the window.name, right? So what has actually happened here is a DOM clobbering. Your child window was able to replace the actual secure_flag global variable in the parent window by changing its name to secure flag, which created a new global variable in the parent window. Yeah. So another interesting. So yeah, of course, you can find these global variables by using Hookish and just give me the global variables. It just tells you what are the global variables which are listed in the current page. Now, redirecting parent window with while opening links in a new tab. So sometime back, a guy called Daniel reported on HackerOne, which was a vulnerability on HackerOne and different other websites where you can have a parent window open a new tab with a target equals under blank, then it can be malicious. And if he does a window.opener.location.reload of some phishing page, then the original page just changes its domain. So, which can be pretty useful in phishing attacks. So here's the attack, which the guy. So this is a page which has, okay, click me, I'm this, which has an underscore blank, which opens in the new tab. So when someone clicks that, as you can see here, this was the original page, which was from this window, which was a completely different domain. You were able to change the original page's window. So this can be used in classical attacks like tab nabbing, which browsers by default try to prevent when you do a normal window.open. But this is a case in Chrome and Firefox when you do open tabs using underscore blank. So yeah, so the way to prevent this would be to use to make sure before redirecting you set the window.opener to null, or to make sure that your new tab has rel equals no refresh set to it. Yeah. So yeah, so that's why one of the things HackerOne does right now is to set all these things, set things to null before redirecting to different pages. So it can be interesting if you're doing it in the context of web apps like banking apps, where if someone navigates away and then comes back and sees a login page, they might think, okay, this is the login page of the bank which I was already on, but in fact you are on a different domain, a classical phishing attack. So why is this interesting? So when I wanted to test for these kind of vulnerabilities, I was looking into the task is basically to look into pages and look, okay, give me the links which has target equals underscore blank and doesn't have rel equals no refresh. But static analysis is pretty bad at doing that, because by default, in most of the cases, I've seen developers have the links already being populated in the HTML, and then they have some jQuery code which loads on window.load, and then tries to inject underscore blank and rel equals no refresh on the load. So here you need to dynamically understand the DOM and dynamically parse the DOM and then get the results. So this can be possible only by using some dynamic analysis tools like Hookish. Okay, here's the final one, and a pretty interesting one, and one of the problems with ECMAScript 5's methods, which I'm going to talk about. So I found this vulnerability in in a couple of templating engines, which are not so quite popular, but yeah, and also in custom implementation of templating engines. So to talk about front-end templating engines, so you have some data, a custom data, and then you have a templating language, something like, okay, data.mark, which opens like this, which has tags like this. Then the template compiler understands, okay, I need to replace this word with this. It's pretty simple, right? So if you are a templating engine developer, and if you're trying to do that in JavaScript on the front end, the natural way would be to load the template data object, try to do all the filtering and encoding, and then find whatever is your templating language's pattern, and do a simple string.replace of pattern and the matching data. So here's a simple templating code which I'm going to talk about. So assume for the sake of this demo, like the actual input HTML is the first line with the placeholder, which is the templating directive here. So me as a templating engine, this do templating is going to replace, whenever I say placeholder, I'm going to replace that with a certain value. So in this case, I'm going to replace that with the input which the user gave. So and before doing the string.replace inner HTML.replace of input HTML.replace of placeholder comma input, I'm going to do a filtering, and the filtering is a pretty standard HTML filtering where you take care of single quotes, double quotes, less than, greater than, stuff like that. So let's take a look at an example. Yeah. So yeah, here's the input to the templating engine. So whatever you give here, so if I say src equals some small orange dot blah 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 dot png, then yeah, this is the actual templating code which was generated, and it just writes into the document dot, it just does a document dot write and puts that into the current DOM. So here, we can actually cause an XSS in this scenario, but let's take a look at that. So if you try to do things like 1, 2, 3, single quotes, double quotes, blah blah blah, whatever, all these are being filtered because the templating engine already does a filtering, right? So as you already know, to get out of this context, you need to have a single quote to get out of this context because your placeholder ends with a single quote. So if you can have a single quote, you can get past that and have standard XSS code like on load equals or on error equals blah blah blah. But we already have filtering here in this case. So the actual payload that can bypass this would be something like $, and a backtick on error equals alert of yeah. So in this case, I'm using a couple of interesting characters here. Of course, the first one is $, which is pretty interesting in this context, and then backtick. Yeah, backticks in general are, for a long time have been considered bad, but in front-end templating engine encodings, you don't usually see things like backticks until unless if the template engine writer is aware of things like mutation XSS and knows things like MXSS can cause different bugs, he's going to replace stuff like that. But yeah, in a traditional filtering, you're not going to look at things like backticks or $. So if you do templating of that, I'm not so sure how many can see this, but yeah, this can actually get past the single quote without using a single quote. So let's see what happened here. So of course the culprit here is the input HTML.replace, and this was the bypass that we used. So what's happening here is ECMAScript's definition has few interesting ways of doing stuff, and one of them is the string.prototype.replace. So usually when you write a string.replace, every language gives you, okay, tell me the string to search for and let me replace with that. There's no special conditions. But in case of JavaScript, which uses ECMAScript, which uses ECMAScript standard, you have something like special cases with $. If your text to be replaced starts with $, then it can take different behaviors. Then you can do different behaviors. So here the interesting behavior that we made use of was $, and a backtick. So the $, and the backtick would replace the current string with whatever was there before the current context. So here we made use of the single quote, which actually started the context that we were in, and we were able to use the same characters even though they were being filtered. Yeah. So yeah, so these kind of things can be directly found using tools like Hookish. So the whole idea here is we need to start thinking in terms of identifying bugs in the front end, not just by looking at traditional DOM XSS, but also different nuances like this. These are not just the simple nuances, but there are like tons of them. There are tons of examples of DOM clobbering, few which can bypass important security restrictions and the way people do code on the front end today. So yeah. So the next thing I'm working on with respect to Hookish is, of course, improving the track of how we track data between the source and sinks. Of course, I'm trying to patch Chromium to make sure that all these properties which have been recently, the location property can be overridden again, and track more things like post messages, and easily identify or have a library or a framework to identify especially interesting cases like DOM clobbering. So yeah, that's what I've been working on, and yeah, do contribute and make use of this tool. Of course, criticize as you wish. It's on github.com/skepticfx Hookish. It's a Chrome extension. Of course, every Chrome extensions are open source, and I would love it if someone comes and talks more about this, and build tools like this and start pen testing or looking for these kind of bugs. Yeah. Any questions? Thank you.